Thank you so much. Hello, everyone. Today, I'm presenting our paper titled A Comparative Study of Large Language Models for Goal Model Extraction, written by me and my supervisors, Sanaa Alwidian and Masoud Makrehchi for the SAM conference. The first stage of the software development lifecycle is the requirements engineering stage, which determines the success of the subsequent stages, namely design and code. One approach to software development that is widely followed is agile methodology, where user requirements are collected using user stories. These user stories are semi-structured pieces of text that represent stakeholders' intention, role, and rationale for their requirement. A user story template takes the following format. As a who, I want or I need something so that and a rationale is provided. It contains the what, which is the expectation from the envisioned system, who wants it, and why the feature is important. The fact that they are snippets of text written in natural language, which is why they are easy to comprehend, and this has led to the widespread use of user stories for eliciting requirements. Goal modeling languages such as GRL, which is the focus of this paper, is part of the URN standards that is employed to organize these user stories and reveal how they are related to one another. This language enables requirements engineers to model stakeholders' objectives, different ways to achieve them, and their positive or negative impacts on various quality aspects of the envisioned system. However, manually extracting goal models from user stories and constructing goal models is a tedious process. The challenge stems from various reasons, including granularity mismatch. User stories are generally formulated at lower level of abstraction, focusing on specific functionalities. On the other hand, goal models are created at higher level of abstraction to capture the higher level objectives. Therefore, bridging the gap between the granular user stories and the high-level goal models is challenging. Additionally, converting user stories into well-formulated goals is challenging because it involves extracting hidden goals, decomposing them into sub-goals and tasks, which depends on the skills of the requirements engineer. Also, not aligning them with the goal modeling grammar or goal modeling principles adds to the complexity of the process. Current goal modeling tools such as US2 Star and R2 rely on manual heuristics and NLP-based techniques that lack contextual understanding of the user stories. Although they extract the why and the what parts of the user story, they fail to establish the relationships between them due to the heuristic limitations. This relationship understanding is crucial for revealing the hidden goals and subtasks. Additionally, handcrafted rules may overlook the nuances in the natural language, leading to inaccurate extractions that can lead to misinterpreted requirements. Another study that is quite close to our work is work by Chen and team that address the concept of automatic creation of GRL goal models using LLMs. Their approach, however, used a single prompt to generate the entire goal model. However, we believe that this leads to a less comprehensive goal model. To provide a rationale for our work, we provide an illustrative example. We assigned the user stories that's shown in figure 1A to 3 graduate students proficient in goal modeling and directed them to create goal models. The stories are adopted from the literature, so the domain is well known to the students. The 3 distinct goal models created by them are shown in figure 1B. All these manually generated models are interpreted differently by each of the students, leading to varying levels of granularity in terms of intentional elements and their relationships. Also, the second goal model lacks many implicit goals, which are also called as soft goals, and the models also do not show interactions between between different goals in terms of dependency links and contribution links. These inconsistencies cause conflict when finalizing the appropriate goal model for the given user stories. We intend to evaluate the natural language capabilities of three popular LLMs, GPT-4, Llama, and Cohere, in identifying these implicit goals from the user stories. Furthermore, we aim to assess their ability to tweak the levels of abstraction to refine the granularity of the goal model and identify dependencies between various goals mentioned in the user stories. While a typical approach often implies a single goal, single prompt strategy with few shot learning to generate responses, we hypothesize that similar to arithmetic reasoning problems, the task of generating goal models also needs multiple step reasoning methodology. And this cannot be built in using a single prompt technique. This is because typically a human goal modeler follows a set of sequential steps when creating a goal model. Initially, the modeler extracts actors from the user stories, followed by identifying the goals, the soft goals, and the required resources. In the third step, he pinpoints the tasks and the subtasks necessary for achieving this established goals. The final 4 steps involve establishing various relationships, including the means end relationships, contribution links, decomposition links, and the dependency links. Intuitively, the LLM must also adhere to the same sequence of steps in the same order to arrive at a goal model. So that's why we propose the multi-step iterative prompting technique to facilitate this process. The 7-step iterative prompting strategy enables the LLM to build a goal model iteratively. This technique is inspired from the chain of thought prompting technique that dissects the complex problem into manageable intermediate steps. The first step of the approach is the GRL model generation phase that begins with the start prompt. The prompt consists of 3 key elements. The first segment of the prompt is the contextual background. It provides the LLM with the information necessary for understanding the problem at hand. In our case, this includes a detailed description of goal-oriented requirements language, GRL. It also included a brief definition outlining all the intentional elements and their relationships. Additionally, we mentioned that the LLM is assigned the role of a requirements engineer who understands stakeholders' needs. This way, we ensure that the LLM understands the purpose of the prompt and aligns its responses to our goal. The second segment of the prompt is a set of user stories for which the goal model extraction is needed. The last segment of the prompt serves as the output specification. And this defines the characteristics of the LLM's output. Here, we provided 3 instances of the outputs generated by a goal modeling visualization tool, GCM-Nav, as few short examples. These examples allow LLM to learn and replicate the structure so that it can be visualized using the GCM-Nav tool. The next set of 7 steps form the multi-step prompting process that guide the LLM through each stage of goal modeling creation. The first 3 steps here provide brief instruction to analyze the previous response and identify the hidden actors, goals, and tasks. The following 4 prompts encourage the LLM to find the interconnections. That is the means end, decomposition, contribution, and dependency links. Our approach maintains a chat history at each step of the iteration, which is called as chat context. This consists of the previous prompts and the responses generated. This chat history is passed to the LLM while it generates the subsequent responses. Is the GRL model visualization phase. The XML representation of the GRL model obtained in the first phase needs to be imported manually into the Juicium Now tool for visualization. However, we observed instances where the XML generated by the LLM contains malformed elements in it, and these discrepancies failed the LLM generated goal models to be imported successfully into the Juicium Now tool. So to prevent such import errors, we implemented a Python-based XML validator. The validator model just checks the XML representation of the model, but it still does not guarantee whether the model is visualizable in the Juicium Now tool. If the XML validator finds no errors in the XML generated, then the XML representation is deemed ready for visualization in the Juicium Now tool. We conducted experiments to address the following research questions. Are popular LLMs capable of producing a goal model for a set of user stories? If so, which LLM is recommended for undertaking this task? And secondly, how do the goal models generated by LLMs semantically differ from those developed by the requirements engineer? The LLMs that we chose are GPT-4, Llama 13, Chat, and Cohere 4.3. We also conducted an ablation study to see the impact of the temperature on the various number of intentional elements extracted. For this, we chose 3 temperature values, 0.4, 0.6, and 0.8. To evaluate the RQ1, we took 10 goal models from the literature, where these models are validated and well known in the goal modeling literature. The data that we adopted from the literature included the goal models and the snippets of the requirements that were not in the form of user stories. Therefore, we transformed them Okay, so we transformed them into the format of user stories. And this helped us to independently evaluate without relying on the domain experts. And for the syntactic evaluation, we also computed the syntactic score that contains the total number of intentional elements in the generated responses. Coming to the semantic evaluation, we utilized an existing data set of user stories, and we computed, we identified the issues in the LM-generated goal models and categorized them into 4 categories: semantic correctness, understandability, adherence to the standards, and general issues. Now, let's go over the syntactic evaluation of the GPT goal model. So the goal model shown here is for the user story shown in the motivational example, and the syntactic score is 35. On the other hand, the syntactic score of the manually generated goal model is only 12. This is because the LLM identified many hidden actors, such as row traffic engineers, and many hidden goals. It also created tasks such as create visualizations for the simulation results that contributed to higher syntactic score. We also noticed that setting the higher temperature, such as 0.8, is apt for goal model generation task using the GPT-4. Coming to the Llama model, Llama worked similar to the GPT-4. Its syntactic score is comparable to GPT-4 with and it contains and syntactic score is 37. And it extracted several hidden tasks, subtasks, such as testing user interaction, designing user stories, and so on. So this means that the open source LLM, Llama, is as efficient as the closed source LLM, such as GPT-4 for the goal modeling task. Coming to the Cohere model, the GRL model generated by the Cohere is very poor when compared to the GPT-4 and the Llama. It is even worse than the manually generated goal models. So therefore, we do not recommend Cohere to be used for extracting intentional elements and interconnections for the user stories. When we did semantic evaluation of these LLM-generated goal models, several issues were identified, such as terminology misalignment, hallucinations, and LLM not paying attention to the numerical details present in the requirements. And these semantic evaluation exposed several issues in the generated goal models. So, so this shows that setting the higher temperature for the goal model generation task reduces the constraints, and it allows the LLM to rely on its knowledge about the problem domain. It helps to decompose the higher level goals and soft goals. Therefore, the task we recommend for the goal model generation task, we recommend a higher temperature such as 0.6 or 0.8. However, the semantic analysis revealed several issues, such as creation of incorrect goal models, inability to detect ambiguous user stories, variations in the outputs for the same user stories and the same prompt, and also limit on the context length of the LLM. So, of course, we acknowledge two threats to validity. First is related to the bias in the user stories chosen for this study. And secondly, there is subjectivity involved in the manual evaluation of the outputs of the LLMs. So in this study, we explored the potential of using LLMs for goal model generation task. We also analyzed the influence of temperature parameter on the number of intentional elements extracted. We find that the GPT-4 and Llama with with temperature of 0.8 is more useful in generating goal models that are acceptable. This approach not only builds the abstraction gap between the user stories and the goal models, but also encourages stakeholders to avail the assistance of LLMs. Our syntactic and semantic evaluation finds that employing LLMs for producing goal models is, although is a promising task, it suffers from many issues, such as incorrect goal models due to LLMs' limited attention, inability to detect ambiguous user stories, and limited context length. Therefore, we recommend LLMs to be used as assistants to domain experts in generating the goal models. And of course, the manually generated goal models are superior to the LLM generated ones. Thank you, everyone. I welcome any questions or discussions.